Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our webinar. We're featuring Xiaoguang Sun, who will be presenting on specialty fiber for distributed temperature and strain sensing from OFS. OFS, of course, has been a very active member and has been a leading provider for fiber optic sensing. We look forward to hearing your presentation. Thank you.
Thanks, Mark. I'm Xiaoguang Sun. I'm a R&D engineer in OFS Specialty Fiber Division. Thanks, FOSA, for inviting OFS to give this webinar. So we're going to talk about some of the specialty fibers for distributed temperature and strain sensing made by OFS. So this is an outline. First, I will give a short introduction to OFS Avon and our specialty fiber capability. Then we'll look at the two fibers. One is the multimode graded index optical fiber for 1550 nanometer distributed temperature sensing with the bandwidth optimized at 1550 nanometer. Another one is a dual-Brillouin-peak fiber for Brillouin-based distributed temperature and strain sensing. Then we will look at a multi-core fiber, especially some multi-core fiber capabilities from OFS, and a dual-core multimode graded index fiber for Raman-based DTS measurement with a turnaround. OFS Avon is located in Avon, Connecticut. We have 145 employees with 14,000 square meters of facility area. We have 6 jaw towers, 3 cable lines, 3 environmental controlled rooms, and we also have plating for preform machining and the grating writing capabilities. We are ISO 9001 certified. What makes Avon special is that our business model is we develop and manufacture products that enable our customers to manage light in harsh and technical challenging environment. We are vertically integrated. We have capability from making preform for the fiber, cable the fiber, and make a final assembly to the customer. We have a very high product mix, and each product typically have very short manufacture runs. Each of the products typically have very unique features to meet the different requirements. For example, in the medical application, in the defense and aerospace sensing, industrial and oil gas sensing, etc. This is an illustration of OFS Avon specialty fiber manufacture process. This is a preform. We have a preform manufacturing and machining groups, so we can make single mode, multi-mode, multi-core fiber preforms. The preform is put into the furnace and melted and pulled to the desired diameter. The diameter can be from 70 micron to 1500 micron diameter. We have diameter monitoring and defect detector on the tower. We can put different coating on the fiber, including UV or thermally cured coatings, including acrylic, HCS, silicone, and polyimide, etc. We have inline coating diameter and the concentration monitor to detect the defect too. Furthermore, we have inline extruder. We can put additional buffer on fiber to have more protection to the buffer. The buffer material include ETFE, nylon, PEEK, and PFA, etc. The fiber then can be taken up with spools. We have a test reliability department. We can further test the fiber in different environment, predict the lifetime, etc. First, we'll talk about the 1550 nanometer bandwidth optimized the multimode optical fiber, GI optical fiber. So this fiber has 15 micron core diameter, 0.2 NA with a bandwidth optimized at 1550 nanometer. So the application is for distributed temperature sensing at 1550 nanometer. The benefit of this using the fiber is it can have high spatial resolution over long distance. This will enable the end customer to distinguish adjacent thermal event more easily in the long distance. So first, I will give a short background introduction to Raman-based DTS. At the bottom here, we show if we send the light into the optical fiber, some light will be backscattered. If we look at the spectrum of the backscattered light, we see in the middle where the wavelengths not shifted, that's really scattered light. On the right, the wavelengths get shifted longer. The Stokes light has two components, Brillouin and Raman. On the left, where the wavelengths get shifted shorter, it's the anti-Stokes signal. It also has Raman and Brillouin signal. So Raman-based DTS utilizes the Raman's backscatter Stokes. We know the Raman-Stokes intensity depends on the temperature. When the temperature rises, both the anti-Stokes signal and the Raman and Stokes signal will change intensity. The anti-Stokes signal change intensity more faster than the Stokes signal. So by measuring these two intensities, we can calculate the temperature. In the middle, we plot the detected signal of the Stokes signal and anti-Stokes signal. We can see it's rolling off just like OTDR. We calculate the temperature by the intensity ratio of the two signals. Usually, Raman DTS use multimode grid index optical fiber, so it can launch much higher pulse power because it's a large area and the nonlinear threshold is much higher. We know in multimode optical fiber, it has many modes, and the mode traveling at a different group velocity. And this will spread the input pulse, and the pulse width will increase with the fiber length. We know the spatial resolution of the DTS system or OTDR depend on the group velocity here, pulse width divided by 2. So when the pulse width increases, the spatial resolution is going to get worse. On the right here, we plotted some index profile of a grid index multimode fiber. So the grid index fiber index typically follow this equation. It has a dependence of L over alpha power. We know the pulse broadening of this grid index fiber depends on alpha. The optimal alpha at 850 nanometers is 2.027, and it's 1.871 at 1550 nanometer for 0.2 NA grid index fiber. We know OM3 and OM4 fiber has very high bandwidth at 850 typically. For example, it has 3,000 megahertz kilometer at 850 nanometer. But if we use this fiber at 1550, the bandwidth only is about 500 megahertz kilometer. So on the right, to illustrate this idea, we plot the pulse width versus wavelength for different alpha. The blue one is a fiber optimized for 850 with alpha equals 2.027. We can see that 850 is a minimum pulse broadening. But if you use this fiber at 1550 here, the pulse broadening is going to be very big, more than 10 times the pulse broadening at 850. This purple one is the pulse broadening for a fiber with alpha equals 1.871, optimized for 1550. We can see the pulse broadening is fairly small at 1550. That means if in a DTS system you use OM3 and OM4 fiber at 1550 in long distance, it's not ideal because of pulse broadening. We made a preform, use MCVD process, and we choose 120 kilometer fiber and cut fiber to 8.8 kilometers and measure the bandwidth. And the bandwidth result is showing here on the right in this table. We can see at 1550, the minimum bandwidth can reach 18 GHz/km with a median of 4.2 GHz/km. With minimum bandwidth of 1.8 GHz, that means the pulse broadening is less than 4 nanoseconds in over 10 km fiber. On the left, we also plotted the bandwidth at different wavelengths. As we can see, the 1550 band is very high. At 850, it becomes smaller, just as predicted in the theory. Then we measure the pulse broadening with overfill conditions using the 1550 nanometer GI fiber and OM4 fiber. On the left is a setup. So we have a 1550 nanometer diode laser. It's going to send out 10 nanosecond pulse width. And here we make sure it's overfill launching condition to a 32 km fiber. Then at the end of the 32 km, we put the in-gas detector there with 1.5 GHz bandwidth. And here is measured the band pulse shape. The green one is the red one is a launching pulse. You can see it's 10 nanosecond pulse width. The blue dot one is the pulse output pulse with 1550 nanometer optimized fiber. The pulse width is about 15 nanoseconds. The black one here is we use 32 km OM4 fiber. We can see the pulse broaden to about 15 nanoseconds. So we see significant pulse broadening with longer fiber. Then we experimentally evaluated the spatial resolution using GI multimode optical fiber using a Raman-based OTDR. This is a setup. So this is a Raman-based OTDR. The wavelength is 1550 nanometer with 0.1 nanometer full wave half maximum width. The pulse width is about 30 nanoseconds. So that means it should have 3 meter spatial resolution. Then we connect the launching to 32 km fiber, either OM4 fiber or the 1550 nanometer grid enhanced fiber. Then 100 meter fiber putting the silver oven at 50 degrees C. At the end, the 330 meters fiber we put back into room temperature at 20 degrees C. So both these two fiber, OM4 fiber, 1550 nanometer fiber, has 50 micron core diameter, 0.2 NA, and 0.4 dB per kilometer loss at 1550. So that means the bandwidth difference is the only factor affecting the spatial resolution analysis. This is the result of the spatial resolution measurement. So we measure the temperature versus distance near the input of 100 meter fiber. We see here the fiber is at the 20 degrees C, and here it's changed to 50 degrees C. So the spatial resolution typically is calculated from the 10% of change to 90% of change. We can see here we have about 3 meter spatial resolution. That means the pulse broadening for 1550 GI fiber is negligible in 32 kilometers. If we use the OM4 fiber, here's the result. Again, this is temperature, this is distance. We can see the transition is much slower. If we calculate the spatial resolution, that's about 10 meters. That means the spatial resolution works about 2 by 7 meters. We see significant pulse broadening. So in summary, the index profile of a GI multimode optical fiber can be modified to minimize the intermodal pulse broadening. And this fiber is also interoperable with regular 50 micron cores with its geometries, numerical apertures, and losses. The bandwidth is higher at 1550 nanometer. with a median bandwidth of 4,000 microkilometers. The spatial resolution of the DTS measurement is less than 3 meters in 32 kilometer distance at 1550 nanometer. So next we're going to talk about the dual-Brillouin-peak optical fiber for distributed temperature and strain application. So this fiber is a single mode optical fiber, but with multiple Brillouin peaks. As we mentioned, its application is mainly for Brillouin-based distributed temperature and strain sensing, and then the temperature and strain measurement need to be separated. The benefit of using the fiber is the measurement can be done using only one fiber instead of multiple fibers, or using intensity Brillouin or Raman-Brillouin combination to separate temperature and strain. And this can be also a simpler setup than using multi-core fiber or few-mode fibers. And using this fiber going to enable us to using simpler cable structures in installation, potentially lower the cost. So this is a short introduction to the background of Brillouin-based temperature and strain measurement. On the right again, it's the illustration. We send the light to the optical fiber. The backscatter light has this Brillouin component. Depending on the temperature and strain, the frequency of the backscatter Brillouin light is going to shift. But the problem is because of this frequency shift depends on both temperature and strain, so we don't know what's the contribution from temperature and the strain, so we need to distinguish the contribution. Typically, single mode step index fiber has only one peak, so that won't work. But some fiber has multiple peaks, as shown here. There's a few fiber with multiple peaks, like leaf fiber, fluorine doped high delta fiber, and the PCF fiber. If you look at all this Brillouin gain spectrum, you can see it has a main peak and it has several sub-peaks. The main peaks is much higher than the sub-peaks. We can use this fiber for distinguish temperature strain measurement using this equation. Here, T and epsilon is the temperature change and strain change. Delta mu1 and mu2 is the frequency shift of the first peak or second peak. C is the temperature coefficient and the strain coefficient of the two peaks. Here at the bottom, we plot the gain spectrum of the leaf fiber again. We see the main peak, first peak, second peak, and the third peak. At the right, we plotted the calculated Brillouin frequency shift at different distance. We can see the green, white, and the red. If we calculate the standard deviation of the measured Brillouin frequency, we see for the first peak, the standard deviation is about 0.12 megahertz. For the second peak, is 0.6 megahertz. For the third peak, is 1.2 megahertz. So the error of the measured Brillouin frequency increases when the intensity decreases. Then if we use this equation to calculate the temperature and strain, the uncertainty will be much higher. So we need to design the fiber to solve this problem. So we have two considerations. One is the gains of the peaks should be at a similar level. We know in single mode optical fibers, it has many acoustic modes, but because the overlap of the optical field with the higher acoustic mode, the other peaks can be very small. So we need to increase the overlap integral of the optical field with a higher order acoustic field, and also decrease the overlap integral of the optical field with the fundamental acoustic mode. Secondly, we need to increase the difference of temperature and strain coefficient to make this term as big as possible to reduce the measurement error. So we know if we put different dopant in the optical cores, the Brillouin frequency shift and the temperature coefficient can be changed. So on the right, we plot some of the Brillouin frequency shift versus temperature of different fibers. The x-axis is the temperature, y-axis is the Brillouin frequency shift. We can see for some fiber, the Brillouin frequency shift is about 10.5 GHz at room temperature. Some fiber can be 11.5 GHz. Also, the temperature coefficient is quite different. For example, this one is 0.7 microns per degree, and some of this is about 1.5 microns per degree. This all depends on dopant. So this is our first fiber. On the left is the optical and acoustic index profile. So this fiber has two steps. It has a core diameter 4.7 with numerical aperture 0.12. So the center region from 0.0 to 2.2 micron is doped with germanium and fluorine. The outer region, 2.2 micron to 4.7 micron, is doped only with germanium. So if we look at the optical index, it has one step, but the acoustic index has two steps. If you look at the simulated LP1 optical field, it's black line, and the LP01 and LP03 acoustic field is this dashed lines. We can see the overlap between the optical field, the black one, and the fundamental mode, LOP1 acoustic mode, is much smaller. Using this, we can calculate the Brillouin gain spectrum here. This is simulated Brillouin gain spectrum. We can see it when it has three peaks, LP01 and LP03 and LP02. Then we made a preform and choose the preform to a fiber. And this is the measurement Brillouin gain spectrum. We can see it's very similar to the predicted one. We have three peaks. The highest two peak, the intensity is very close. It's only difference about 2%. We also measure the fiber properties. So the mode field diameter is about 10 micron at 1550. The cutoff is 1430. The loss is about 0.2 dB per kilometer. So it's very similar to regular single mode fiber. We also measure the temperature and strain coefficient of this fiber. On the left is the measure the temperature coefficient. The x-axis is the temperature, y-axis is the relative Brillouin frequency shift for peak 1 and peak 2. The calculated temperature coefficient is 1.14 and 1.06. So the difference is 0.05 microns per degree, which is twice as that of a traditional leaf fiber. We also measured the strain coefficient, x-axis strain, y-axis relative Brillouin frequency shift. The coefficient of the two peaks is very close. To further increase the temperature coefficient difference, we made a second fiber with just the core composition, and this is the simulated Brillouin spectrum. We can see now it has only two peaks. This from LP01 and this from LP02 acoustic mode. It has 500 megahertz separation, so it's a little bit larger. On the right is to measure the Brillouin frequency shift gain spectrum. So the two peaks is at 9.89 and 10.398, so separate about 500 megahertz. The peak difference is very close. It's less than 0.4 dB. But this fiber has slightly smaller cores, and the mode field diameter is about 7.2 micron. and the cutoff is 12, 10 nanometer. The fiber loss is slightly higher, it's about 0.434 dB per kilometer. Then we measure the temperature and the shrink coefficient. Here again, on the left is the temperature coefficient of the two peaks. X-axis is the temperature, y-axis is the relative Brillouin frequency shift. The temperature and shrink coefficient, the temperature coefficient is about 0.911 microns per degree and 1.1 microns per degree. So the difference is 0.2 microns per degree. It's much larger than before. And the shrink coefficient on the right is also shows the peak. The coefficient is at 0.041 per microstring and 0.047 per microstring. That's quite different. We need further increase the difference of the temperature to reduce the shrink coefficient to reduce the measurement error. Here's an experiment done by NETL to simultaneously measure the temperature and strain. They use 1 meter fiber held at constant tension, about 1.1%, and they changed the temperature from 62 degrees and 72 degrees. On the left is the measure the temperature result. X-axis distance, y-axis temperature. The blue one is when the temperature is at 62 degrees, and the red one is when the fiber is 72 degrees. The standard deviation of the measurement result is only about 0.5 degrees C. On the right is the measured strain at the two different temperatures. Because at the two measurements, the fiber it was held at the same strain, we can see it's almost the same. The standard deviation is about 13 microstream, so this probably is good enough for some applications. So in summary, we have designed and manufactured single mode fibers with multiple Brillouin peaks. The peaks have close matched intensity and large separations. The difference of the temperature coefficients is also increased to reduce the measurement error. We need to put additional dopant to increase the difference of the temperature coefficient. Next, we're going to talk about the multicore fibers. A multicore fiber is an optical fiber that contains multiple cores inside a single cladding coating. OFS has a long history of making multicore fibers, starting from year 2000. This is a link to our website about our multicore capabilities. On the right is some examples of the interface pictures of the multicore fiber we made. This is a 8-core multimode graded linear fiber for data communication. This is a 4-core single mode fiber for long-haul subsea communication. This is a 7-core single mode fiber in medical application for safe sensing. As we mentioned, we have an in-house preform manufacturer and machining capability, so we have a lot flexibility in making preforms. We can make a preform in rod in tube method, basically that's a drill blend preform, insert a core rod, then the preform can be consolidated, or we can collapse the preform in furnace during job. We can also make the preform using stack and draw method. Basically, we assemble the glass core, rod, and calculate into appropriate shape, and then we can draw it. As an example of multi-core fiber, we'll talk about a dual-core fiber for DTS. This is a dual multimode core fiber. The application is for dual-ended DTS system to correct the temperature measurement error caused by the wavelength dependent loss. What we mean by wavelength dependent loss is shown in this equation. We know the temperature in DTS is calculated by the ratio of the intensity of anti-Stokes signal to Stokes signal. It's here R, and this is the wavelength of the Stokes signal and anti-Stokes signal. This is a temperature-dependent term, but it also has a term of the loss at the anti-Stokes signal and Stokes signal of the distance between your launching and the position. So because loss of the anti-Stokes signal and Stokes signal are different, and depend on the position, this term can be changed. It's different. So there's going to be error associated with the measurement because this term, this is we call the wavelength dependent loss. Wavelength dependent loss can be caused by Rayleigh scattering, which is 1/λ4. So the wavelength dependent loss at 1100 nanometer and 1000 nanometer can be 0.3 dB per kilometer, caused by Rayleigh scattering. Also, hydrogen radiation and connector and splicing can induce this wavelength dependent loss. The benefit of using dual-core fiber is because of the compactness, it can fit into very tight space. So it can save cable space and save cable weight and easier to deploy. So this illustrates what is the difference between single-ended and dual-ended measurement. On the right is a single-ended measurement. Basically, the fiber is laid along the distance. You send the light into the fiber and get measured reflected light to calculate the temperature along the lens. For dual-ended DTS system, you lay two fibers parallel to each other in the connected end, and you interrogate the signal from this end, then from this end. Then you do a geometry average of the measure the ratio of the acoustic signal to Stokes signal, and you get this equation to calculate the temperature. Again, this is the temperature dependent term, and for dual-ended system, the wavelength dependent loss become like this. So this term is no longer distance dependent, and it becomes a constant. So it can be calibrated and removed from the calibration. So the temperature error can be removed. As an example of the distributed temperature measurement using single-ended and dual-ended method, we plot a temperature measurement on this graph. The blue line is the result using single-ended measurement. All the fiber is maintained at room temperature about 22 degrees C. We can see the temperature error get bigger and bigger with the length. The x-axis is length, y-axis is measured temperature. We can see at the end of the 10 kilometer, the measurement error is about 8 degrees. If you use dual-ended setup, the measurement is much more constant. As showing this is orange line. It's constant, so the result is much more accurate. This is our dual-core multimode fiber. It has two 50-micron pore diameter pores, and A is 0.2. The center-to-center distance about 100 micron. It has 2.25 micron glass cladding, so it's a lot more robust than 125 micron glass fiber. The large distance can minimize core-to-core crosstalk. Again, this preform is made using rod in tube method. We drill 2 holes and put the core on. The fiber is further coated with 260 micron polyimide coating, so this fiber is suitable for high temperature application. This is the end-phase picture of the multi-core fiber taken by optical microscope with fiber illuminated from both ends. This is 2 cores, this is cladding. We also put a turnaround at the end of this end of the dual-core fiber. as illustrated in this graph. So this is our two-core fiber. The turnaround is made of a quarter pitch grid index fiber. At the end of the grid index fiber, we put high reflective coating on it. You can see here, the light from the core one will exit from core one, expand and collimate at the end of the quarter pitch green fiber, and reflected and focused back to core 2. So this is very small. It's only about 1 millimeter long and 225 micron in diameter. So it's all fused, so no sections under stress, so it can be more reliable. And it can also achieve very low loss. And all this section is polyimide recoated, so relatively robust. Here is a picture of the turnaround under microscope. On the left is the dual-core polyimide coated fiber. Here's the splice between the dual-core and green. This is a green fiber. On the right is a picture of the turnaround with a US 1 cent coin. This white line is the turnaround. You can see it's quite small. Next, measure the loss of a turnaround at 1064 nanometer using a Raman DTS. Here, the axis is the distance, y is the intensity. We can see the insertion loss here is less than 0.3 dB, but we see about 2 dB reflection 1 meter before and after the turnaround. This reflection may affect the temperature measurement. We also see a little bit reflection at about 30 meters before and after turnaround. This reflection typically will not affect the temperature measurement data. We also measure the spectral loss of the turnaround. We launch broadband light from one core to another using a fan out. Here's a plot of the insertion loss. X-axis is a wavelength, y-axis is loss. We can see from 80 nanometer to 1250 nanometer, loss less than 0.4 dB. And this low loss region covers those anti-stoke signal if we use 10.60 nanometer pump light. We also measure the loss at high temperature and plotted here. The x-axis is a time, y-axis is the temperature or the change in the insertion loss. We can see here the temperature is changing from room temperature to 300 degrees C and maintained for about 24 hours, then cool down. And the red line is a change in the insertion loss. We can see it's less than 0.4 dB and 0.02 dB. So the change was negligible. Then we did a DTS measurement with a dual-core fiber with turnaround. This is our setup. On the left is a Raman DTS. This fan out to launch the light in the two cores. The first 1200 meters is put into room temperature. Then we put 40 meters into a thermal oven, another 40 meter at room temperature, and the last 40 meter was turned around and put in the thermal oven again. The thermal oven was set to 315 degrees C. This is the measurement result. Again, x-axis is the distance, y-axis is the temperature. We can see this is the first 40 kilometer in the oven, then the 40 meter out of the oven at room temperature. This is the last 40 meter inside the oven with turnaround. Because of the reflection, we see about 1 meter data was compromised around the turnaround, and we didn't see any other negative effect. So in summary, dual-core fiber with integrated turnaround can be used for dual-ended DTS measurement to remove the wavelength-dependent loss. The miniature turnaround with polyimide coating is suited for high temperature sensing application up to 300 degrees C. So in summary, I showed some specialty fibers for distributed temperature and strain sensing. Specialty fiber can be designed to provide some benefit in distributed temperature and strain sensing compared with using commercial available fiber. The benefit including it can fit fiber into confined space to save light, to simplify cable structure, and increase the accuracy of the measurement, and also the resolution of the measurement, or reach longer distance. Thank you, everybody, for your attention.
Well, thank you for a very informative presentation. We already have some questions, but for those who want to add some additional questions, there is, of course, the chat box with appropriately questions on the right of your screen where you can type in a question. Sort of kicking things off, one of the issues that people kind of doing comparison with different types of fiber, what are the benefits of dual core fibers when two separate fibers can be used for dual-ended DTS measurements? Could you do a comparison on that?
Yes. So dual core fiber, one is it's very compact because the core is very it's always connected to each other. So the length, like excess length cost area, can be reduced. Also, this fiber can fit into very small compact spaces. We have a customer. They want to measure the temperature using dual-ended system, but they need to put the fiber inside a very small tube, less than 1 millimeter. So if they use two fibers, they have to use a very big fiber to put the turnaround in. So using the dual core fiber, they can use a 1 millimeter fiber cable, and they can save the weight by about 75%. I think another customer also use dual core fiber in oil well temperature measurement. Before they have to pump a single core fiber down the oil well through the U-turn and pump the fiber back. So this is very time consuming, and sometimes the fiber breaks. If they use dual core fiber, they can just pump the fiber down to the end, and that's it. They can save a lot of time at the installation.
Okay, that next one is fairly, can dual core fiber be used for strain measurement?
If we use single mode fiber, we can. Typically, multimode fiber, we don't use it for temperature strain measurement. We do have different dual core single mode fiber available.
So the next one is a fairly technical. Fiber design 2 is indeed interesting to reduce the temperature strain dependency, but the loss of 4 dB is very high. So the question is it possible to come up with fiber that it would not have a loss, would have a loss in the range of basically 0.2 dB?
Yes, that's what we are working on. So the second one, because we have the smaller core diameter, so we put a lot of germanium in it. We can, if we look at the first one, it has about 0.2 dB per kilometer. So we can make something between the first one and second one to make the fiber loss between 0.25 to 3 dB, 0.3 dB maybe. We have to try it to answer that question. That's a very good question.
So next question is how can dual core fiber be spliced, and what is the splice loss?
Typically, we use PN pipe slicer because you need to rotate the core to match the fiber on the left and the right. I think a lot of splicers have this function, both from OFS and AFL. The splice loss for the dual-core multimode fiber is typically less than 0.1 dB, and the splice time is less than 1 minute.
Okay, let me get. How can your dual peak fiber help customers do temperature and strain sensing measurement?
Yeah, I think using this fiber mainly to distinguish the strain and the temperature measurement. For example, we have a customer they used to measure the bridge integrity. Before they have to measure both temperature and strain. For temperature, they use a Raman DTS, and they're using a multimode fiber, and they use another Brillouin interrogator to measure strain. So they have to deploy two cables and need to make sure the two cables are close to each other. When they do the measurement, they have to carry two instruments to the site. Now they can just use one single fiber and one interrogator. This can save them a lot of time and upfront cost.
So next one is for strain and temperature sensing with Brillouin system. Does it matter whether the temperature or strain coefficients are different?
Yes, it has to be different because if the two peaks shift at the similar rate, you won't be able to distinguish the shift coming from either temperature or strain. If you look at this equation, that means if the shift is same, this becomes 0. That means your error is going to be infinitely large. That means you can make the measurement.
Okay, so instead of dealing with the turnaround device manufacturing and handling the complexity, why not use twice longer fiber to achieve the double-ended measurement?
Oh, yes, people use that. A lot of people use that. Some people use a turnaround, but the problem is in harsh environment, the turnaround is less reliable and much bigger. For example, that's a turnaround is about 3 millimeter. Basically, it's a fiber bent to 3 millimeter. So the fiber has a lot of stress, so it's very easily get damaged. So like in application, like in all temperature measurement, when the fiber breaks, the turnaround breaks, it's going to be cost a lot of effort to replace it.
Let me see. I think I have all the questions. We've done turnaround, core fiber. Well, let me give you a more open-ended question. Besides compactness, are there other benefits of using multicolor fiber for just in distributed sensing?
I would say yes, depending on the situation. You have to look at into the whole sensing system, look at the interrogator, look at the packaging especially. Usually fiber has to be cabled in it. So how easy to cable it? For example, people use two fibers for distributed strain and temperature sensing. So in this setup, they have to make sure one fiber is completely strain-free to separate the temperature and strain. So that's not easy to get done. So using multi-core fiber or dual-Brillouin-peak fiber can solve that. Also, the installation, as we mentioned, using multi-core fiber probably can save some installation time and also long-term reliability. If you look at the turnaround too.
Okay, I think that's very helpful. For folks with more detailed questions, we probably should go back to your contact information and encourage people to get in touch with you directly, but I think I've gotten to the end of all the questions. As we typically get asked, we were asked, when will the webinar be posted on the YouTube page for those people who want to go back through it again. And usually that takes a day or two unless we end up with a technical glitch, but we've been pretty consistent on that. That is on the fiber optic sensing page on YouTube. So thank you very much for a very informative presentation, and that concludes today's webinar.
Thank you. Thanks, Robert.